Okay, this is the second installment of part 2 of my argument that causal determinism is an illusion. And I'm giving evidence from physics. So I've already talked about how the notion of space-time seems to indicate that cause and effect is an artificial concept and not fundamental to the nature of space-time. I've also talked about electrodynamics and the nature of electromagnetic forces, which also suggests the same thing, that past and future should not be distinguished. At least there's a way to look at electrodynamics where past and future is not distinguished. Then I looked at minimization principles in mechanics, that is, in the motion of particles, which shows that it appears that the path or motion of particles under the influence of forces is determined by a minimization principle, but this minimization principle would require knowledge both of the past and of the future. So all of these seem to indicate that past and future do not play the role that we seem to think they do, and that the distinction between past and future is simply due to our perspective and not due to the underlying structure of the physical world. So this was the last slide that I showed, relating the motion of particles to minimization principles, in particular this least action principle. I should mention that this principle determines the motion of classical particles, that is, particles that we deal with on a daily basis. Particles are objects. They obey this principle. And usually, the fact that this principle works is chalked down to mathematical convenience or mathematical coincidence, because the thought is that the future position of the object couldn't possibly determine the path that the object takes to get there. But I'm not so sure. Now, in quantum mechanics, you don't use minimization principles, but you use a similar principle that also involves the action. Quantum mechanics, or the motion of quantum mechanical particles, that is, very small particles, elementary particles like electrons and protons, the motion of these particles can be deduced from an action principle which is based on the sum over possible paths between space-time points A and B. So let me briefly indicate what that means. So let me switch over to my handy-dandy picture. So here represents the position of a particle at a particular time, and I'll just call that time t equals 0. Physicists like to do that because it makes things simple. I mean, I can say that this is the time when I start my watch, and then this is a potential position of the particle at a later time, which I'll call capital T. Now, in quantum mechanics, it's impossible to chart exactly the path of a particle. However, in order to get the probability of passing from this position to this position, what you do is you sum over all possible paths from this position, and these are paths in space-time, because here my time direction is this way. They're paths in space-time. Each one of these paths has an action, and the probability of going from here to here is a sum, and that sum involves the action for each of these paths. So from this path I compute the action, that gives me one term in the sum, and then from this path I compute the action, I use that to get another term in the sum. I sum over all these actions, and that gives me a probability of going from this position to this position. Now, it's a little more complicated than that, but that's the basic idea. You do have to sum over all possible paths in order to get the probability of going from here to here. Right. Now, I would like to point out that action principles are not just fundamental in quantum mechanics, but also in quantum field theory, which is the next step up. Quantum mechanics assumes a fixed number of particles. Quantum field theory explains the creation and annihilation of particles. So it explains the weird stuff that goes on in quantum particle accelerators. So we have to say that these action principles are really quite fundamental in higher physics theory. Now, the fact that the action principles involve a sum seems to indicate there may be an underlying process that involves summing. Okay, this is similar to the argument I gave before that the principles that involve minimums seem to indicate a process of minimization. So here I'm arguing that the sum involved in action principle indicates there's some process of summing. But again, this can't be a process in time because the process presupposes where the particle will end up in the future. So there is some indication that there's some kind of process outside of space and time whose result gives me the probability of a particle moving from here to there. Now let me close off this discussion with some more quantum weirdness. I'm going to talk about a quantum game show. Now really this game show is a way of representing an actual experiment called the EPR experiment. EPR stands for Einstein, Podolsky, Rosen, who thought up conceptually this type of experiment. And you actually perform the experiment with photons. But in order to make it more easy to visualize, I'm going to phrase it as a game show. Okay, so suppose the host in this game show shows you 3 doors. The 3 doors are left, middle, and right. And then you have a partner, and the game show host shows 3 other doors to your partner. So the partner also gets to see 3 doors left, middle, and right. Behind each door is either a car or a goat. And you and your partner each get to open one of your doors. And then the game starts over. Now, of course, in real life, you would accumulate cars and goats, but I'm just using this as an illustration. But you get to play this game indefinitely. And remember, you get to choose freely which door you want to choose. And you also want to keep track of what happens whenever you open which door. Now, it turns out that whenever you and your partner both open the same door, you always get the same result. And you've tried this and tested it again and again and again. If you open the left door, you get a goat, and your partner also opens the left door, he'll also get a goat. So it seems that the game show host is putting the same thing for you and your partner. It seems that whatever he puts behind your 3 doors, he puts the same thing behind the 3 doors of your partner. So that seems something that's unmistakable. So what you'd like to do is discover what proportion of time is there a car behind both the left and the right doors. Right. This host is not obliged to put the car and the goat with equal probability. You don't know beforehand what the probabilities are. But you get to play the game indefinitely, so you should be able to tell what the proportion is. And of course, you get to choose in such a way that the host can't tell what you're going to choose. You get to choose at the very last minute. You can change your mind the instant before you open the door. So the host shouldn't know what choice you're going to make. Okay, so based on your observations, and you've played this hundreds and thousands of times, you can see that whenever you choose the left door and your partner chooses the middle door, you both get cars 10% of the time. Okay. And whenever you choose the middle door and your partner chooses the right door, then you get a goat and he gets a car 10% of the time. So let me represent these probabilities with a diagram. Right, what I've drawn here is a diagram that indicates all the possibilities for the middle car, the middle door rather. Now the middle door is either a car, which is the left-hand side here, or a goat, which is the right-hand side here. So I'm drawing a set diagram or Venn diagram you probably saw in high school. So this left-hand side represents all the possibilities when the middle door is a car, and this right-hand side represents all the possibilities when the middle door is a goat. Now, you found that middle car and left car takes place 10% of the time. So that's why I've labeled this region here by 10%. This is the set where both the middle car, both the middle door is a car and the left door is a car. Now we also saw that the right car, middle goat, was 10%. So I've taken this region and labeled that 10%. So the set where both the right door is a car and the middle door is a goat, that's also 10%. So notice something here. We've only checked 2 doors in this purple set. What about the third door? What about the right door? Well, that could be either a goat or a car, and we don't know what proportion of time. However, we do know that the proportion of time that you have left, right, and middle, all cars, must be less than 10%, because it would be a set within this purple set. Furthermore, we know that the set where we have left door and right door have cars and the middle door has goat must also be less than 10%, because that would be contained in this green set. Right? This green set says the right door is a car, the middle door is a goat. We don't know about the left door, but it must be contained in this set. So the possibility of having the left and right door have cars and the middle door have goat, this must be less than 10%. All right, now look, either the middle door is a car or a goat, and we've covered both those possibilities. Okay, so if you just look at the left and right being cars, we've covered all the cases. If the left and right are both cars, either the middle is a car or the middle is a goat. So we've covered both of those possibilities. So the probability that the left and the right doors give cars must be less than 20%. Right? That's what we can calculate from our probabilities. And this is, I'm not pulling a trick on you. This is perfectly valid mathematics. You can think about it, work it out. But this is actually true. If things are going as we think, there should be less than 20% of the time that you get left and right cars. But that's not what happens. What actually happens is you get left and right cars 30% of the time. If you check the left door and he checks the right door, you get both their cars 30% of the time. So what's going on? Now, the only way that the host could pull this off, it seems, is if he figured out what your choice was. Now, again, you can do everything you want to not to tip him off. But somehow it seems that he must know what your choice is. Now, the other option is that he doesn't know, but both the players and the host are being coordinated somehow together in ways that they don't understand. Okay? So this second option is the option that I'm saying is consistent with the fact that there are causes outside of space and time. The dealer doesn't cause this to happen. If he caused it to happen, he would have to know in advance what your choices are. So he'd have to be clairvoyant. So if you eliminate that possibility, the only other possibility is that both the host and the players must be coordinated together. And that coordination must be somehow outside of the process of space and time. I need to say there are other explanations in the physics community for this experiment. There's a theory called Bohmian quantum mechanics that the choice of the goat or car is guided by an ethereal pilot wave that basically gives the host the power of clairvoyance. Transactional quantum mechanics says that each gameplay is really a two-way transaction between the host and the players. There's some kind of mysterious handshake going on that makes them always agree. The Copenhagen or consistent histories interpretation, which is probably the most common, says there's only a goat or a car behind doors that you open. If you don't open the door, then what's behind is simply undefined, and it's not worth even asking what's behind. So the argument was predicated on that fact that there were definite objects behind the doors that weren't opened. So if you take away that assumption, then you can explain the results. Now there's an even weirder result called the many worlds interpretation, which says that the host doesn't actually choose a goat or a car, he only chooses a set of possibilities. And once the players actually look behind the doors, these possibilities are actualized, all possibilities are actualized in different parallel universes. But the possibilities for each player will depend on the other player's choice. So I'm not going to go deeply into this, but you can see that there are some very strange interpretations. And the most common one is just to sort of wash your hands and say, well, this doesn't apply. But I would like to say that the idea that there are causes outside of space and time fit very neatly with this real-life experiment in quantum mechanics. Okay, that's it for this video. In my next video, when I get it together, we claim that something else is going on behind the scenes. That is, the entire game is the outcome of an extra temporal process outside of space and time. So we'll show how this approach can explain not just these experiments, but several mysterious quantum properties. And that this gives us a theory that's mathematically consistent with the accepted theory, and also gives us an experiment that can possibly test whether the theory is right and show differences between our theory and the conventional theory of quantum mechanics. All right, thanks very much for watching.